Log on, tune in, find out. Another good idea from Cambridge.
You invite me at this program, and thanks for giving me the opportunity to talk about my work. Then the title, KL Stability, has a subtitle. Grassmannian. Then the first thing, some notation. In this case, X always is an algebraic and projected curve of genus G at least 3 over C. And I will denote by M and D to the moduli space of stable bundles of stable vector bundles with rank n and degree d. And if I fix the determinant, then I'm going to write M and C, and the theorem that I want to prove in this talk is as follows. If R is between those numbers and the rank is less than the diagonality of X, then for a general point E in the moduli space and C, there exists a morphism C to the Grassmannian n minus R at the moduli space and C. In fact, this morphism is an embedding and the image of this morphism contains E. I mean, the idea is try to describe some geometry about the moduli space, and the idea is define some Grassmannian in the moduli space. And
what is M and E?
The moduli space of vector bundles with rank n and degree d. Okay, fix. Sorry, fix the determinant. Is that right? Okay. Then, as I said, the idea is try to describe, in some sense, the geometry of the moduli space, introducing the Grassmannian, and this way. To do that, it's necessary begin with the KL stability, because the stability, KL stability, will be the property and useful property to describe that Grassmannian. Then, the first thing that I want to do is talk about the KL stability. In the second, I want to talk about the Heck modification and the third, I want to construct the Heck Grassmannian. Well, then I'm going to start. In the first, I'm going to define what means KL stability, and then let K and L integers and E a vector bundle over X. Then is KL stable if for also bundle F of E, we have the following inequality: the degree of E plus K minus L over the rank of E is bigger than to the degree of F plus K over the rank of F. Then KL stability means that if you have the stability, then you can put the integers in these quotients and see what happens with that.
What's the L?
Sorry?
The L you haven't used it.
K minus L, yes? I'm sorry for my. Then at this quotient, I'm going to denote by MKF. When K is a number, then in this case, I have that this number is K minus L of E. And this inequality is equivalent that to have that the n K minus R of E is less than to the m minus L of the quotient E over F. It's similar, it's the same thing. Then, with this definition, we have that with this definition, we have the following properties about the KL stability. And some properties are, the first is, in general, if E is KL stable, then E tensor L is KL stable for any line bundle L. The second is the dual is LK stable. Here the integral switch. And the third is that E is K minus A L minus B stable, where A and B are integers and positive. Then these properties are direct of the definition. Oh, I'm sorry. And well, the first thing is that I need to prove that the existence of the KL stable bundles. Then I have a theorem that says that if K and L are such that k n minus 1 plus L is bigger than n minus 1 G, or k plus L n minus 1 is bigger than n minus 1 G times G, then there is not vector bundle KL stable. I'm going to write this that this how the NLD is empty, where A, K, L, and D is the set of the isomorphic classes of vector bundles Kn and stable. With rank n and degree d. In the second, if K and L are such that
The first one is empty? Or
empty, I'm sorry, yes, thank you. Then such that K n minus 1 plus L is less than or equal to n minus 1, G minus 1, and K plus N minus 1 less than. Then in this case, we have vector bundle, KL stable vector bundle. In this case, it's not empty. That is a numerical condition for the existence. And I can draw a picture where if I take K and L, in this case, then the theorem says that I have two lines where for every point over the lines, then the set is empty, and I have another line where the set is not empty. In fact, I can find a region where the KL stability implies the stability. Then I have something like this in this region that I call R1. Then always the KL stability implies stability for any point in this region. Then now I know where exists the KL stable bundles, then I can work with them. And well, why KL stability? Because the reason of the KL stability is that the KL stability is the good property to preserve the stability in the Heck modification. That is the reason for the KL stability, maybe. Then, well, I'm going to say what means Heck modification, and what is the relation between the Heck modification and the KL stability. Then I have the Heck modification. In this case, I take a vector bundle as before, and then I fix a point in the curve, and then if B is a subspace of the fiber EX, then I can obtain an exact sequence of coherent chips where the kernel is in fact a vector bundle, and EV is called a head modification of E defined by the pair X and B. In this case, if E is an stable bundle, that not means that EV is stable. Then, no, in general. In general, we don't have this property. Then, what can I do with EV? Well, if I'm not sure if the EV is stable, then I try to do another head modification, but now using EV dual. Then if W is in a subspace of EV dual, then I can do the same construction and obtain another vector bundle here that I call EVW. And the properties for these vector bundles are the determinant of EV is the determinant of E tensor of minus Rx if is an minus R dimensional subspace. And if W is also n minus R dimensional, then the determinant of EVW is the determinant of E minus 1 in this case. Then we have the following lemma, which says what is the relation between the KL stability and the head modification, and the lemma says that if E is KL stable, then EV is KL minus R stable, and EVW in this case is chi minus R L minus R stable. Then, in particular, that means that if
Have you dualized properly there? You haven't switched the K and L round.
Yes, sorry. Here, okay, in this case, sorry. Then, in particular, if E's are stable with R the same number there, then EV and EVW are stable in particular. Then we have that to obtain a stable vector bundle under head modification, we need the KL stability in this sense. Then now we have the following theorem. That says that let E an stable vector bundle here with the determinant fixed and K plus L is bigger than R or equal and
I'm sorry, you mean
yes,
EV is not stable, right?
sorry,
EV is R0 stable, right?
in fact, is R0 state bundle, but there are, I'm going to write this here. We have the 0 stable is the same thing that is stable, and in this case, remember that there is one property that says that if one vector bundle is K stable, then it's K minus E A L minus B stable. Then in this case, how R is positive, then that implies that EV and EVW are stable. Then if R is less than the monality of X, then if E is KL stable, let me write how I have fixed the determinant. I want to write with the determinant fixed too. And then there exists a morphism defined by the vector bundle at the point X and one point X to go from the Grassmannian EX and N minus R to the moduli space N minus. In this case, how I have, if I take a subspace here, then I can associate the class of the vector bundle given by the modification in this subspace and given by the point X in this case. Then the construction for this morphism.
So your curve is a smooth.
Yeah.
And
Sorry, I didn't say that.
Oh, yeah, maybe you said that, but also just to make sure, your Hecke modification does not depend on the point little x, does it? I think it doesn't, but I'm not sure.
You can move the point and then you can construct another Grassmannian, sorry. Then if you take another point, then you can obtain another Grassmannian in that sense. In this sense, no?
And it will be different. Yes. Yeah. It does depend on the point.
Should be different. Then the construction of this morphism is as follows. To construct the morphism, then I call only by G the Grassmannian minus R, and then I have over G. I know that I have the trivial bundle with fiber the fiber of the vector bundle, and then here I have an exact sequence of this type, and then I can give an morphism induced by EX, where if I take one point here, then I send to the XG, and here I have the pullback of the vector bundle, and then I can describe with this morphism and immorphism here from this pullback this coherent sheaf, and as this morphism is subjective, then this is subjective also, and then I have the kernel here, and this family of vector bundles give me the morphism of classification to the moduli space where for every subspace I have the modification here. Then this is the form that of construct the morphism, but now how I can prove that this morphism is in fact an embedding, then I need to prove that this morphism is injective and his differential is injective too. Then to prove injectivity, we need first the following lemma. Okay. This lemma says that under the hypothesis of the theorem, then we have that if F is a Heck modification of E defined by the point X and the subspace B, then H0 of the of F to E, it's exactly 1. To prove this lemma, then the first thing that I need to see is that if I have an amorphism F to E, then
I'm sorry, what are you doing with x times g?
sorry,
What is the x times g for? You really mean x times g?
X times G? No. Maybe here?
Yeah.
No. I send 1 point at the how I have fixed the point, then every point that I take here goes to a point on X. How I in the product, then
X what product?
X times G.
Okay, what is that?
G
Why do
goes
you-
with 9. G is a Grassmann unit.
Yeah, but why do you, what, I mean, what do you mean the Grassmannian bundle? I mean, you really want the
Fixed
product?
Grassmann.
No. This is an vector space only, and then I take the Grassmannian.
Why do you take that product?
I take a product here.
Huh?
Want to prove that you have a family of stable bundles and you have
I need a family of vector bundles over X parameterized by this.
Oh, I see. So you're going
Then-
to I see. You're going to make a universal family on that.
In this case, if you fix one point in G, then you have the extension.
I see.
Okay.
Okay. I see. Sorry.
Yeah.
I thought you were going to move the point, but you're not moving the point.
No. The point is fixed.
All right.
Yeah. Then, well, I have this lemma, and if I have a morphism from F to I, then this morphism is of maximal rank. Because if this morphism is not of maximal rank, then I can have then the morphism factors by a morphism H, and this morphism is of maximal rank. And then using the Kähler stability of E and how F is an Heck modification, then F is in fact KL minus R stable. Then using the properties of KL stability for E and the KL minus R stability of F, we can prove that it's not possible to have an anamorphism which are not stable using only this diagram. Yes, for example, we have that in this case, the E prime is a sub-bundle of E, then we have that this inequality. And in this case, the rank is the same for those vector bundle, and the degree change only by R. Then we have K minus L plus R of F. And using again the definition of KL stability, this is less than minus L plus R of F prime. But using that this is of maximal rank, then we have that this is less or equal to minus L plus R. And this is a contradiction to the K plus L is bigger than R, using these integers. And then, in fact, the morphism is of maximal rank. And now, to prove this, we have that if F is a morphism, then we can take F. We can take this, and using again that this is the modification, that F is a modification, that this means that we have a morphism here, and this means that the morphism is 0 only in the point X, and the multiplicity of the 0 is exactly R, using the gonality. And then if I take two morphisms here, then for a different point Y, then exists two values where this is not an isomorphism, And this says that then the morphism is 0 in the point y, and this is a contradiction again. Then we have that there is only one morphism up to scalar product. Okay, then this means that if I take,
Sorry, could you just repeat where you used the gonality?
I'm sorry?
Could you just repeat again where you used the gonality assumption?
That the degree of the morphism, to x, no, sorry. That if you have a line bundle with,
¿Dónde lo usas?
You've hidden it behind this board.
okay. Maybe here, if you don't have the gonality, then maybe you can obtain 0 here in other point different to x. But this is not possible because we have that this morphism is 0 only in x. Yes? Okay. If you have this morphism is not an isomorphism, and then you can take the morphism. This goes to the determinant at this, and then is 0 in y in this case. But this is not possible because this is 0 only in x, and the multiplicity is exactly r. Then this will be a contradiction in this case. Yes. Then, now to show that the morphism is an embedding, we have that we need to show that if I have phi ex to the Grassmannian G at the moduli space x, then I take the tangent. If I fix one point in the Grassmannian, the tangent here is I'm going to take a point here and with B here. Then we have the tangent in the point B is exactly the arm of B, it's B. And the tangent here in the image of the B is the H1 of the endomorphism EB. But Narasimhan and Ramanan proved that this morphism can be factors by H0 to EB of EB to EX sense of OX, where this morphism is a boundary map. Then if I want to prove that this is injective, then I'm going to prove that this is injective and also this is injective. Well, then the injectivity of this morphism is direct because we have, if I take the exact sequence defined by the point G, then I have this exact sequence, and then this means that I have an surjective morphism here with the kernel I, and then we can dualize and take the tensor product, and then we have that the homomorphism to B EXB goes to the homomorphism to EBX, EBX to EXB. Yes? Okay, but in this case, to have an amorphism between this vector bundle at this chief, then we have that is defined only in the point X, and if it's enough to have an amorphism here in the fiber to can define amorphism here, then we have the H0 of the EV, EX, EV is the same, or R is morphic to this. But this is injective, then we have that this is injective too. And to have this, the injectivity for the boundary map, then we have also take an exact sequence the exact sequence that I want that I need to take is take the EV to E and then this define an exact sequence of H0x AB dual tensor EB to the H0 to the AB of E to the H0 to the tensor of X, and here we have the boundary map to the H1 of the endomorphism of EB. And then in this case, how the vector bundle is k stable, the property k plus L greater than R means that this is an unstable vector bundle, EB is stable, then this is the same that C. Now the last lemma says that we have only one morphism here, then this is C2, and then means that this is injective. But this is precisely this morphism, and then we have the injectivity for those maps. Then the conclusion is that this is injective. And that means that we have an embedding with this morphism. Then, when I start, I say that I need that the image of the morphism contains the vector bundle E, but in this case, we are in another moduli space. I need return to the same moduli space that I begin. Then for that, I need to do another heck modification. And then, following the the same construction, we have that if maybe as lemma, we have that if is a vector bundle stable, and in this case, I need that k plus L are bigger than 2R to do a double Hecke modification, and the same, the gonality of X is less than R, then if E is an unstable vector bundle with determinant fixed, then we have a morphism, but in this case I'm going to take the morphism defined by the first Hecke modification, defined by EB, in the same point X, and then this Grassmannian goes to XB dual N minus R, and well, we can see that in fact this goes to the E minus 1, but I can take the dual to arrive at the same moduli space, and then in this case, if I take a subspace W, then I'm going to take the dual of the Hecke modification of EB, and then using the last theorem, then we have that this is an embedding. And well, we can, the image of this Grassmannian contains the point E, because if I have the case W equal to B dual, then in this case EB B dual is exactly the point that I take in the beginning. Then this is say that the image contains the point E, and then I define by in this case I define the Hecke Grassmannian as taking the morphism, fix a point, and fix a vector bundle, then the image of these Grassmannians is defined by Hecke Grassmannian. Then, well, the following question is, you take a point fixed all the time, but what happens if you change the point? Then you can take another point, and in fact you can take all the points and do the same construction. Not exactly the same, but the idea is as the last one. In this case, we take a vector bundle here, and I take the Grassmannian of E, and in this case, I can, the idea to construct the morphism is obtain a family parameterized by G, then now I need another family, but in this case the construction is take the Grassmannian of E, and I'm going to give this Grassmannian by the following morphism. In this case, if I call pi to this morphism, then if I take 1 point here, I'm going to change to the pi of G, and in this case, I can do the same, take the pullback of E with, but in this case I need to take the chief over the divisor dg, where dg is the image of this morphism. And then make the torsion.
You're taking the Grassmann bundle now? And I don't understand this map from Grassi to X cross Grassi.
Varies the point.
So it is a Grassmann bundle you're taking, right?
Yeah.
The universal object is Grassi itself.
Then one shouldn't call it G but X.
I didn't get it, sorry.
No.
So you're taking the Grassmann bundle and then again taking the product of the curve?
Yes.
This is, I'm going to take the product, but in this case, I'm going to take the product with the pullback of the tautological here, where the tautological is defined here. Yes. In fact, I have, I don't know, the tautological here, the projection. Yes, and then to define this morphism in a canonical way, I need to define it first here. Here, this is like maybe here in this point, and we have the same.
That one is just
Here is not the pullback. This is only defined in the image of the. It's like yeah, it's the skycraft shift with support in the divisor dg. Yes. But this is this defines my family, and then I can construct. I can do the same construction here, but in this case, we don't have the point fixed. We can move the point. Yeah, I don't fix the point, and then I think that I can do the same construction using this. Yeah, the other thing that I'm working now is try to the. Well, I have morphism to go the Grassmannian at the modular space. Then I want to study the morphism in general for the Grassmannian at the modular space. I want to see how are these morphism in general, and try to say something about this morphism using the morphism that I construct here. Well, there are many questions after to that. For example, another question is, if I have the modular space and I take a point, then if I take two points, then the question if there exists a Grassmannian which contains at those points, or if maybe if there exists some Grassmannian which contains in this way that point. But well, I work in that now, And well, that is all that I want to say. Thank you.